Matt Leifer and Markus Mueller. Welcome to the podcast.
Thank you.
Hi, thanks for having us.
So I'd like to start by asking some light questions, perhaps starting with the relationship between you two. Do you know each other? If so, for how long? And is there any anecdotes you want to share about each other? Maybe Matt can start.
I don't know about any anecdotes, but we have known each other for quite a long time. We both were postdoc perimeter. I mean, we may probably have met before that, but I'm not sure. But anyway, we've known of each other for a long time, and have worked on some similar areas. Particularly things like generalized probabilistic theories. We've both done work in that area. Anecdotes, I'm not so sure on. Can you think of anything, Marcus?
Well, not so sure about literal anecdotes between the two of us, but yes, we've been at Perimeter Institute at the same time. We were probably both at the chain bond sometimes together. I do remember you at Perimeter and me, and I was more coming from a kind of mathematical physics corner, and it's more like over the years, the months and years, I began to appreciate more and more what you've done. So in retrospect, I feel I should have taught more at Perimeter. I should have addressed you more because you did some really interesting things in the foundations of quantum information. But as you said, we worked also on a couple of things that we both worked on, probabilistic theories and so on. And we've met every once in a while and discussed, and it's always been a pleasure.
Yeah, I actually remember that one time we were at a conference in Brazil, the contextuality conference, and I was walking, somewhere with you, and you said that you had this amazing project, this sort of magnum opus, right, that you were very excited about. I believe that was this project that you were talking about in your episode with the algorithmic information and stuff like that. So I remember when you being very, very excited about that stuff when you first.
Yeah, exactly. I'm sure I called it crazy, not amazing, but
yeah, crazy.
And you said you have something like that too in the back of your head, but not sure what you meant back then. Anyways.
Yeah, so I guess if you haven't met each other in the previous month, the last time of your encounter is through the podcast, the previous episodes, listening to each other's episodes. Do you want to share some impressions about each other's episodes? What do you think? Is there anything from the other person's answers that surprised you, Matt?
I mean, surprise, I don't know about surprise, but, I think that you'll find that we end up agreeing about more stuff than it might appear, right? I think one of the things that came through is, despite the fact that we're maybe pursuing different directions and different sort of kinds of technical results, we're both kind of a bit non-committal fundamentally, right? So you might have thought, okay, Marcus is a hardcore idealist, anti-realist kind of person, and I'm a hardcore realist, and so we're going to completely disagree on everything. But that's not really true. I mean, I think we're both more interested in sort of the pragmatic aspects of these approaches and what you can sort of get out of thinking that way. So I think that, to me, that came through more strongly from Marcus's episode than I would have expected.
Yeah, I think I agree with this. I guess even methodologically, there's so much we agree on, like what makes sense to do and what not. And pragmatically proving no-go theorems is often more important than speculating. There's really nothing in Matt's episode where I would strongly disagree with. So I probably in the end, even though that may be bad news for a debate podcast, we might actually agree on a lot of things.
Now, that leaves to a question. What do you expect from this upcoming episode? Do you, I guess, you have a lot of agreements, but is there something you expect to achieve in the debate, Matt?
I mean, if I knew that, there wouldn't be a need for a debate, right? So, I think we should, and we probably do disagree about, algorithmic information theory, algorithmic probability, and its relevance to the foundations of science. We probably disagree on that, even if we like the work that each other is doing. So we might end up talking about sort of the conceptual foundations of that kind of stuff, and there may be something for me to learn there. So that would be an interesting way to go, I think.
Yeah, Mark.
Yeah, that could be a good direction to go, because I think when I talk about algorithmic information theory, it sounds a bit like, oh, I like to see the universe as like a computer, and I want to play around with this kind of notions of Kolmogorov complexity because they're so beautiful. But this is absolutely not the case. It's more you're forced to using this as a tool once you talk about something like concrete data. So when you talk about correlations between experiments, for example, this is typically described by probability theory and an information theory. When you want to look at a single bunch of data and say something about a structure, then you're just forced into that regime of mathematics. But anyway, so in any sense, we'll see where it goes. I agree with Matt that it's not clear than that. Otherwise, there would be no debate necessary. But yeah, perhaps we can clarify each other's views a bit and so on. That would be nice.
Sounds good. So let's then get right into the debate. The first topic is a pretty broad one. It's something that's harder to avoid in any serious discussions of quantum foundations. Is it worth looking for the correct interpretation of quantum theory? And the debates will proceed in rounds. In the first round, I expect short answers, very short answers from each of you. Matt, please start.
Okay, so yes, but there are no interpretations. That's my short answer.
Markus?
No, but it's worth looking at what quantum theory tells us about the world.
Interesting. Now it seems that there's a apparent disagreement. And now in the second round, Matt, please explain your answer.
Okay, so and one of the things is like, with all good foundational questions, one of the alternatives is I reject the question. And so that's sort of what I'm doing here. So it's a very weird thing in a scientific theory to say, oh, here's the practical part of the theory, and then here's its interpretation. And those are two separate things, right? They're not related to each other. And that's kind of what we've tried to do in the physics community with quantum theory. I think that when you look at the interpretation, like really seriously, then it really isn't clear where the dividing line is between interpretation and different theory, right? Now, there are certainly ideas where the road from the basic idea to some kind of empirical prediction is a lot longer, right? The ideas are far more sort of foundational, if you like, and it's going to take a lot of sort of other auxiliary hypothesis to get anything out of it. But I don't really think, I can expound on this for particular interpretations, but I don't really think there is an interpretation of quantum mechanics that is provably equivalent, that any of them are provably equivalent to each other in a sufficiently general circumstance. And at least sort of the dividing line is unclear. Like one key example, for example, of this would be de Broglie-Bohm theory, which in its sort of standard formalism, everybody says, yes, it reproduces quantum mechanics, it's just an interpretation. But it has this non-equilibrium variant, which to my mind is a more natural version of it, which does predict things that are different from quantum mechanics. So according to some people, that's just an interpretation because all it does is make metaphysical statements about what exists in reality and doesn't change the predictions. But according to another point of view, is a different theory. And I think that if you look hard enough, you'll see that with other interpretations. So what I think is that there's a correct way of looking at quantum theory that makes sense, or if not quantum theory, then the theory that comes next after quantum theory. There'll be a correct way of looking at quantum theory that will lead to that. And, as a physicist, I wouldn't really be interested in interpretations of quantum mechanics if I didn't think that was the case. I'm not, I don't dislike metaphysics, but I'm not interested in doing it for the sake of doing it. I'm interested in how do we make progress in our understanding and explanations and predictions in physics. And that's what I think we're doing. So I don't draw this sharp line. There aren't theories and interpretations of theories. There's just sort of the mass of stuff, some of which is more closely connected to experiment than others. So
Good. Now, Markus, you have a chance to explain your own answer.
Yes, so I should probably defend what I meant by no. I mean something quite specific. So I agree a lot with what Matt said. So, for example, there are versions of quantum theory that are not literally interpretations, but do make different predictions. Valentini's version of Bohrmian mechanics, collapse models, and it's worthwhile studying them and putting, say, experimental bounds on their potential range of applicability. But when I now want to talk about interpretations, then for the sake of the argument, I would like to assume that they are predictively equivalent. If we say, in the purest sense, let's talk about interpreting the formalism and not just making predictions. So then, I mean, you can, for example, refer to being a pragmatist as a physicist. Yeah, that's what Matt did when he answered. But I think you can perhaps say more, and that's that sometimes in physics, we've learned that some questions just fundamentally don't have answers. So some things that we intuitively think must be properties of the world or must be answers that are out there, just the questions don't make sense. So for example, relativity, I'm not sure how fitting this example is, but the very simple example, we've learned in relativity that the notion of simultaneity is not fundamental and absolute. So we better just throw out this idea of simultaneity from the way we describe the world. And the question whether two events actually happen at the same time or not does not always have an answer fundamentally. Now, my suspicion is that when we want to decide, for example, between two predictively equivalent versions of quantum theory, say an Everettian-like interpretation and a completely predictively equivalent version of some sort of neo-Copenhagenish view, assuming that they can be predictively equivalent, then one just say, well, maybe even nature hasn't decided. So maybe you're asking a question that just fundamentally doesn't even have an answer because it's not one or the other. It's like a non-question that we're asking. That's at least a possibility. And so perhaps the progress can then be to say, well, maybe we would like to ask different sorts of questions rather than that question.
Good. Now, in the third round onwards, you are free to say whatever you want. For example, you can comment or challenge each other's views. Matt.
Okay, well, I mean, so I gave the easy example earlier, right? So the de Broglie-Bohm theory is an easy example where it can be viewed as either an interpretation or a different theory. But I would go so far to say there are no seriously advocated interpretations of quantum mechanics that are fully equivalent, predictively. So what do I mean by that? So the most tricky example is obviously the one that Markus gave, which is, well, something like many worlds theory versus sort of some neo-Copenhagen type of thing. They're very different in their metaphysics of what they say exists out there in reality, but both camps would argue that what they're doing is just quantum theory, doesn't agree with standard quantum theory in any way. However, I mean, so there are sort of two ways in which you might actually say, well, no, they're not predictively equivalent. So one way is to just look at the structure itself and determine whether there are any sort of inconsistencies or problems, like just contradictions that you can't get around. I mean, that's true of sort of the orthodox interpretation with collapse, contradicts with universality of quantum mechanics, for instance. So that interpretation isn't predictively equivalent because you can't really say it has any predictions. So you could have that kind of internal contradiction. Some people would say, for instance, that Everett has that kind of problem with probabilities. Not everybody agrees. Okay, but maybe these are problems that can be resolved. There's also the question of what happens when you apply the ideas that lead to this interpretation outside its usual domain of applicability, right? So, in the case of many worlds, what many worlds basically says is, okay, we have the Schrodinger equation, we have the wave function, it evolves in time unitarily, and that's it. And they claim that out of that, we can get a picture of multiple classical worlds branching and a probabilistic assignment to the branches in some way. Okay, so let's suppose we buy all that. Then what have you got? You've got a procedure for basically taking any mathematical structure, or at least any mathematical dynamical equation, and without adding anything whatsoever to it, saying what is the empirical content of that in terms of like what will observers who are embedded in that structure see, and what the probabilities are. You have a procedure for determining that, and you can apply that to other theories. You can apply that to classical theories. You can apply that to potential candidates for quantum gravity and so forth. And that will either, and so first of all, if you apply it to something sort of beyond the standard range of quantum mechanics, like some purported quantum gravity theory, for instance, or even like just some generalized probabilistic structure or whatever, it will either agree with the kind of reasoning that you get from Neo-Copenhagen type approaches, or it won't. There's actually no real good reason for expecting it to agree. It leads to very different ideas. So, yes, to that degree, I think it's like very similar to the sort of the Broglie-Bohm case. It's predictively equivalent in the sense provided you restrict the realm, provided you say it's predictively equivalent, providing you're making this set of assumptions about how far we're going to go with this theory. It's not predictively equivalent outside of that range, and I think so. That's I mean, to be honest, I don't think it would be very, very weird if theories that made very, very different statements, like extremely different metaphysical statements about what exists out there and how it behaves, were everywhere predictably equivalent. And I just haven't seen an example in the foundations of quantum mechanics where I really think that's true. So I mean, I know for some people this division between predictively equivalent interpretation versus different theory is supposed to be very clear and very important. But for me, I think it's, all of these, almost every dividing line you can come up with is fuzzy in some way.
So maybe just to follow up on that quickly, I mean, it may be that this division is important, but still vague, right? So you could, so for example, what you pointed at is, I think, something that has to do with going from the theory to the actual experience, the actual physics. So this is still a bit different than saying, am I a realist or not? Is there a correspondence in my interpretation? Do the elements of my theory directly correspond to things in the world? It's a bit less than that. It's about saying, here's my theory, here are its claims. How do I connect this now to actual things I see in a laboratory or in more exotic situations or cosmology or whatever I can come up with, at least as a thought experiment? How do I extract predictions from it? So, and then perhaps the different interpretations disagree on like where they want to put parts of this procedure. So the Everettians would perhaps want to say, well, if you want probabilistic predictions, you shouldn't think of these probabilities as a fundamental part of your theory or if you claim about the world. It's more in the application. Once you really try to bet on the future, then, you extract this as this part of this sort of vague structure in connecting the theory to reality that you see around. Whereas Neo-Copenhagen view would say like this is an integral part of the theory. This is the Born rule It's built in some sense. So when you doubt whether different interpretations can be predictively equivalent at all, and probably rightly so, I think it is difficult to conclude this with certainty. And this difficulty may also come from this vagueness that arises from linking the theory to the actual things we see in the lab.
Yeah, I mean, so the Bohemian people are very fond of saying, what's the quote? It's equivalent to quantum mechanics as far as quantum mechanics is unambiguous, right? Standard quantum mechanics itself is not 100% unambiguous. So there's that too. But yeah, I mean, I'm not insisting that they're not equivalent because I'm a realist and I need to have something that's realist. I'm taking a much more sort of, I want to say it's a sort of pragmatism light kind of approach, right? So I don't want to say I'm committed to pragmatism in the sense of, believing in the theories of William James or anything like that. But what I do want to say is that at least in the realm of science, a scientific truth has to have some pragmatic cash value, because if you can't do anything with it, if you can't use it in an explanation, right? I want to be quite broad about what I mean. I mean, it doesn't necessarily have to be directly a prediction, but if you can't use it to give some kind of explanatory power or make calculations easier for you, or just make thinking about the theory easier, or make a prediction, those kinds of things, then I can't really call that sort of thing a scientific truth, because there are many things that could be true that have no empirical import directly or indirectly whatsoever. So I regard that as a precondition for a scientific truth. So if there is such a thing as a correct interpretation, which I cast doubt on that, it means that there must be one set of ideas that has more utility than the others. So that utility could be in extending the theory outside of its current domain of application. That would still make it the correct interpretation of the theory, because it turned out to be the most useful set of ideas. So yeah, I mean, for me, realism is interesting because one of the pragmatic virtues is explanatory power. And generally speaking, at least prior to quantum mechanics, you could say that part of the explanations that were offered by theories were in terms of things that really existed in the world out there and how they behaved, right? Doing classical electromagnetism is a lot harder if you don't think that there are things called electrons out there and there are things called electromagnetic fields and they behave in this way. You can have other ways of thinking about it, but those ways tend to be less useful. So, what's interesting about realism for me is mostly that we've reached a theory for the first time where, you could always be an anti-realist about theories if you wanted to, but when you were thinking about the theory, you'd say, well, does this theory offer a realist account? And the answer would be yes. And with quantum mechanics, that's not quite so clear. So it's not something I want to throw out with the bathwater, if you would like, because it has been so useful and it has explanatory power. And so if we're going to get rid of realism, we have to make sure that the thing that we replace it with also has that sort of explanatory usefulness. And so one of the criticisms of sort of anti-realist approaches is that you sort of throw out all of your apparatus of explanation. And so that's sort of the main criticism of it. I actually think that, Marcus, what you're trying to do with algorithmic information theory is partially be viewed as a response to that, just partially sort of trying to say, well, let's try and make a structure for explanations for things that doesn't rely on objectively existing outside world. So that's one of the ways I think it's very interesting. But yeah, that's I think I've gone quite far from the original question right now. But yeah.
Yes, Marcus, do you have any urgent replies to this, or
I
please.
think so. Maybe a quick clarification on my view. So I'm not denying that there is an external world, and that it is an important. It would be stupid to ignore this kind of explanation of what we see around us in these terms. So I'm not an anti-realist per se, but I certainly want to hold on all the virtues of realism. That, for example, the fact that we see these regularities around us, that we see this world with its laws and so on. This is not a miracle. Right? So, however, I think that there is a way to see what we call the external world as something that's not in itself fundamental, right? But that can arise as an approximation from something else. Now, that something else is something that you wouldn't intuitively perhaps want to call a world, and I wouldn't even take it seriously if it wouldn't reproduce our usual notion of realism as an approximation, right? But I'm not an anti-realist in that sense that I deny any kind of relevance. Like, certainly, for example, you wouldn't deny that water is a fluid and that you can jump in it and swim in it if you learn someday that it actually supervenes on like molecules and whatnot, right? So you can say, as long as your approach, call it realism or not, reproduces realism and its virtues to good approximation, then it doesn't fall prey to the miracle argument.
Mm-hmm. I mean, I would agree with that. It certainly doesn't fall prey to the. I mean, one of the things is you can view it as a response to the no miracles argument, but I don't know whether I'm happy to call that realism. I mean, it basically. I mean, the reason is what you're trying to say is that the real world as it is, as we normally think about it, is an emergent thing rather than a fundamental thing. So, what is real in the sense of everybody agrees that it's out there is emergent from something and it's not fundamental. And I don't know, I mean, maybe realism is a fraught word, but certainly that's not something that I'm very keen to call realism, because realism seems to be the starting assumption that there's something out there independent of us, and that's what we're trying to explain. That's the thing that we're starting with. Whereas this sort of relegates that to a sort of higher level of emergent level of the ontology. So, I mean, you're right that it's probably not correct to call it anti-realism either, because it's certainly not solipsistic. It's certainly not giving up on any explanation of intersubjective agreement and things like this. But anyway, this is probably just a semantic debate, but I don't know how happy I am to call that a form of realism.
Okay, it seems we are digressing a little bit already.
Yeah.
The original question. So it'd be a good chance to start a new topic, which is related to what we're just discussing. Should we seriously consider a first-person approach to physics?
I think Markus should go first on that.
Yes, Markus. Yes or no?
Yes, quick or slow answer?
Quick
The answer. My quick answer is yes, if it's understood in the right way.
Good. And Matt?
I think my answer is probably the same. Yes, if it's understood in the right way. We may disagree on what the right way is.
Okay, then Markus, please explain your answer.
So I wouldn't want to argue for this just by means of philosophical debate or like general ideas what a good theory would look like, or like personal taste. It is more that you may say, here are a bunch of puzzles and enigmas and thought experiments that I cannot make, that I cannot solve as a matter of principle. If I begin with a third person view and I deny any relevance to a fundamental first person view in some sense. So that's for me the motivation to take it seriously and to try to build a rigorous approach that starts with some sort of notion of the first person. I mean, not consciousness, not humans or anything, but more some abstract version of local data, whatever is locally available to somebody. And what I try to do is to argue and show that it can indeed help solve some of these problems that is shown up, for example, in the cosmology and in foundations of physics, in philosophy, and other fields, right? I can say more about that, but maybe I stop here for now.
Okay. Matt, you have a chance to explain your answer.
Yeah, I mean, okay, so I think there's I can't remember who this phrase comes from, Dawkins or someone like that. We should be open-minded, but not so open-minded that our brains fall out, right? In the case of quantum mechanics, and in the foundation of quantum mechanics in particular, there have been sort of very clearly defined lines drawn, right? You're either a realist or you're an anti-realist, or you either believe that there's something to the sort of neo-Copenhaganish ideas, or you think it's all total rubbish, and you don't have any sort of talking across those lines. Well, the talking across those lines that happens tends to be a lot of talking at each other and sort of misunderstanding the points. So I think that given where we are in the foundation of quantum mechanics, and given the fact that I do think there is a correct interpretation in the sense of correct way of thinking about things that's going to lead to progress, I think it's a good time to try more radical ideas and go down roads less traveled. This is one of the things I admire about Marx's work. He starts from somewhere that's sort of a surprising start. Well, he ends up somewhere surprising given his starting point, because his starting point seems okay. It's very empiricist, and he's going to sort of, perhaps the most sort of interesting thing from the foundations of quantum theory perspective is to just say, well, you end up deriving the fact that there would be the appearance of some mutually agreed upon external reality. Okay, so I know everything's classical in the current approach, but that would be, because the criticism is usually, well, you have no explanatory power whatsoever in your sort of neo-Copenhagenist type of theory. This is kind of indicating that actually, no, there can be an alternative explanatory structure. So we may be able to, combine these things. Like, the question is not just sort of, because a lot of the sort of Copenhagenish approaches are basically, they just throw out a lot of realism. The question is, if we don't believe in this fundamental sort of third party reality, how much of the explanatory structure that we have when we assume that can we retain? And what Marx's work seems to be showing is that more than you might have thought. So even if I don't necessarily agree with the precise technical details of the way he's doing that, and I do think there's something valuable there that can potentially sort of break down the barriers in these debates, because maybe the answer is really somewhere more in the middle. We don't have to just wholesale throw out realism. We can preserve some aspects of it. And so, yeah, that's why I think it's valuable to look at it from these different points of view.
Good. From the third round onwards, you are free to say whatever you want. Marcus.
All right. Yeah, so what I say, so thanks for this, Matt. So I think I just right now I want to say in general that what I've written so far, I've put out one paper, and I put a lot of emphasis on being technically correct and saying as little as possible about anything conceptual that makes it very hard to read. I think that's also makes it easy to misunderstand. So I realized that I have not really done a very good job in explaining the main idea, which is something else than the technical details with which I tried to work it out. So as a comparison, for example, suppose you're in the Middle Ages or so, and for some reason you have the idea that maybe a force is not a force, but it can be somehow mediated by the geometry of space and time. but you're not that smart. So you don't work out exactly like what it should be, and you don't have any experimental guidance, and you're kind of semi-smart. You have this idea, you can work out some consequences and say, depending on how you formulate the details, here are a bunch of things that it could do for you. So you have a certain class of theories, like an idea, like, can you build a theory of that sort? And then you can say, like, what are the ways, and you really can make it happen to actually write down some equations or some structures. So I don't want to talk too long about my approach, and I want to go to other topics in a few minutes, but now maybe just say that there's a very simple idea here, and that's actually very different from how you work it out in detail. So I've worked it out in detail by using this algorithmic information theory and so on. That's not really relevant, and it could be done differently perhaps. So the idea is essentially that instead of thinking that we are embedded structures, we should think of ourselves as unembedded structures. So what can you say if you don't assume a priori that you're embedded in something that hits on you, right? Right. When you work on it, you will realize quickly that this forces you into certain mathematical directions. But I must emphasize it's not an interpretation of quantum theory either. So this is not what it's meant to be. No. But I'm at the moment, just to clarify for those who are interested, before I get to other topics, I'm working on a more digestible, readable explanation of the main idea, which is less technical, and hopefully up soon. Some of it is in collaboration with Calvin McQueen. So whoever is interested right now to read something, please don't read the old paper. It may be too technical and read it. Yes.